please write your name on the chat area again, even if you did it already. I may have not gotten it from the previous time. Good. So today we're gonna start a new chapter. Chapter 14 is the last one. We're only going to cover the first 4 sections, so not the last one. 14.1 through 14.4. Today we're gonna do 14.1, the first one, which is meant as an introduction, and the theme is vector valued functions. Here is the thing. So what we're doing today is gonna be it's gonna look similar to what we were doing a few classes back when we talked about parametric equations. The difference is that now we're gonna be thinking about them differently. So before, when we had a curve given by a parametric equation in the x, the y, and the z, we could think of that as a way of describing a point or an object moving on a curve, right? Like this, like the one we're seeing on the page right now. So let me try to draw on top of it. So essentially, as x and y move, we sort of, the point moves on top of the curve, right? Kind of like I'm doing right now. Right, like that. And so that's one way of thinking about it. The other way of thinking about it is that we don't think of that as the point. We think of those as the vectors. You see these blue vectors that are drawn already on the diagram, right? So you may think that what's really happening is that as t goes on, as time changes, these vectors change. So you start pointing, you start with this one over here. Let me draw on top of it. So you start with this one, and then as the time moves, you start pointing towards more and more, right? And then this one, and then time keeps going. So you just, this vector keeps moving around, right? Pointing in the direction where the particle is moving, where the object is moving. Okay, so that's the main difference that we're gonna be considering today. So we're gonna be talking about parametric vector equations, or you can think of them simply as vector valued functions. All right, so let's go back. Actually, right here, let me just clear these drawings. And then right here, since we have it, so this is how we're going to be denoting it. So right like this. So we have a vector function, a vector valued function. Notice how the R is bold, right? Usually I would put a little arrow on top, but right now in the book, they simply have it as bold. And then what we specify is what is the function for the X component, what is the function for the Y component, and what is the function for the Z component. And these three are functions of T, right? So as T changes, you have a different X, a different Y, and a different Z, and you're thinking about the vector whose head is at that particular point and whose tail is at the origin, right? That's the part that we were just talking about right now, okay? So that's going to be a vector valued function. And the first one, the first kind that we saw, for example, when we're talking about parametric equations, was, for example, the way to think about a circle of radius A centered at the origin. So I'll show you that. Let's go to the page here. So you may remember from when we did parametric equations, one way to parameterize, let me do it the one with, I'm gonna try to parameterize the circle with radius 4. So this is going to be 4. This circle over here, right? And drawn exactly like I just did it right here on the screen. So I was drawing it in this direction, and I started right here, and I went once around, right? So we learned before that one way we could do this, one possible parametrization, was by doing x 4 cosine t and y 4 sine t. That was before when we were doing parametric equations. So the new way of doing it now is to think of this function. This is now a vector function that has 2 components. The x component is this one, and the y component is this one. And this represents a circle of radius 4 traversed once in the positive direction. Now, by positive direction, I mean counterclockwise. So this is always going to be the positive direction for circles, right? Counterclockwise. So this is just a little example of something as it relates to some parametrization, so parametric equations we had seen before, okay? So the new thing here is that we didn't do a lot of examples where our parametric equations were in 3 space. So this one only has x and y, but we may have a z, right? So in general, if you have, if you have something like this, r of t, that has 3 x, a y, and a c, right? Where the t is given between some 2 numbers, between time a and time b. This represents a curve, right? This one represents a curve. In general, this is a vector equation. It's a vector function, a vector valued function that represents a curve in space, in 3-dimensional space, okay? And that's what we're going to be talking about. And we'll start by talking about lines. So one special type of parametrization that we need to learn really, really well, we did already for parametric equations, so this will be a little bit of a review of that, is when we parameterize lines or line segments. So this time, instead of doing parametric equations, what we want to do is learn how to do vector equations, so vector functions that represent lines or line segments. Okay, and for this, we need to remember what we had learned before. So what is it that we had learned before? We learned before that if we have this type of parametric equations, right, where t was going from negative infinity to infinity, these parametric equations were the parametric equations of a line going through the point x0, y0, c0. And maybe we only did it in 2 space. I don't exactly remember. So maybe it was like this, right? Where the b over a was the slope. Well, if we now add a, b, and c, what we get is the direction of a line, right? So this represents a line through the point x0, y0, c0 with direction the same as the vector a, b, All right, so here's the picture that you should have in mind. So remember, we're in a three-dimensional space. Maybe do a little one here. So we're in three-dimensional space. We have this point x0, y0, z0. And we have a line that points in this direction, maybe. So this is a vector ABC. And then what you do is you copy this vector ABC, you put it on top here, and that's the line we're doing. So you want to find out what is the equation or the vector form equation of this line. You just do this. You do x is x0 plus at, y is y0 plus bt, and c is z0 plus ct. Now, this was when we were doing parametric equations. Now, our better way, our easier way of doing it with vectors is just to, compact. See, vectors have this nice property of being able to write down in a concise way, right? Instead of having three things, with three equations that determine the line, we're going to have one. Here it is. So as a vector function, here's how we can write it. We can write R of t is x0 plus at, y0 plus bt, and c0 plus ct. So that's one way. And the way that I like even better is as this. x0 plus y0 plus c0. So that's this vector, right? Plus t times the vector abc. This one I think is the even better one to remember and to know how it works. So that's how we parameterize an entire line. So this is, if you want the entire line, you let t go from negative infinity to infinity. If you only want a segment, then you need to find out what is the t for one of the points and what is the t for the other point. And you just say t between this and that, between this time and that time. All right, I'll clarify that with the following example. So let's take a look at example one. Example one. And we'll do a few problems about this later on today as well. So it says, find a vector function for the line that passes through P, the point 2, negative 1, 4, and Q, the point 3, 0, 6. Okay, so that's what we want to do. And a picture is not terribly necessary, but it helps a little bit. So let's try to come up with our picture here. So put our axis. And we have the point P, which is 2 units this way, 1 unit negative 1 in the opposite direction. So 1 unit here, so we're here, and then 1 unit, or 4 units up. 1, 2, 3, 4. So P is over here. Q is 3 units in the X direction, 3 here, 0 in the Y, nothing, and then 6 up. Okay, my picture was not ideal because Q ends up being over here. And the line we want is this one, right? All right, so we have choices. See, if you look at the way we determine it over here, we need a point on the line, and we have 2, so that's good, right? So just pick one of them. Pick one of them as the point you want to use. So pick a point. Any. You could pick P or you could pick Q. In fact, you could pick the midpoint of P and Q. That would work too. I don't know why you would do it. It would be harder. but just pick one of them. So I'm gonna pick Q. So that's gonna be my x0, y0, c0. So x0, y0, c0 is going to be 306. I picked Q. Well, you could have done it with P, okay? That's not an issue. And then what is it that you do? Then you need the direction vector, right? And then again, here you have choices. Do you want to do the line as a line that is drawn in this direction, going from P to Q, or in the opposite direction, going from Q to P? And again, you have choices, right? So I'm gonna go from Q to P. So direction, for me, my direction vector will be QP, right? So I'm gonna just write here, PQ works too. If you pick PQ, it's just gonna be going in the opposite direction, but it's also valid. It will still be a valid vector function for the line. So I'm gonna pick QP. So what is QP? QP is, remember, we do the head minus the tail. So it's 2 minus 3, -1 minus 0, 4 minus 6. So this is -1, -1, -2. All right? Well, that's ABC. And that's it, right? I have ABC and I have X0, Y0, C0. That's all I needed, right? Looking here. Look, if you look in here, you'll notice that that's exactly what I need, right? I only need X0, Y0, Z0, and ABC. So here's the answer. So the answer is R of t is going to be X0, Y0, Z0 plus t times ABC. In our case, this is 306 plus t times -1, -1, -2. And that's it. That's the one answer, right? I mean, there are other possibilities. If you look at the book, in the book they did it with what is it that they did it? They picked P as a point and they picked the opposite direction, right? So take a look at the one in the book if you wanted to see different ways. Now, so that's, and you should say what is this and what is the range for the t. So here, this is the answer, and t between -infinity and infinity. All right. Now, let's say that I don't want the entire line. I only want the line segment. So that's, I know that's not example one, but let's say we have, but there are some problems in your homework that are like that. So what if we only want the line segment from P to Q, from Q to P? In this case, we'll do it from Q to P, right? Well, to answer that question, you do the same, and the only thing you need to now figure out is what is the T that when you plug it, you get Q, and what is the T when you plug it, you get P. If you answer that question, yes, then you simply say from this this value of T to this other value of T, once you find those two values of T, okay? So what would it be? And the way we did it is, one of them is super easy to know, right? For example, what value of T should I pick so that this expression becomes Q? Remember, Q is 306. So what would be the T, right? And yeah, so Michael is right. 0 works, right? If you plug 0 here, then it's like this is not there. And then you already have one of the points. You already have Q. So note that. So that's one easy one to know. If you plug 0, you get 306. which is what happens when we, so that's one of them, that's Q. How do we get P? So you can solve for what you want, or you can sort of, in this case, it's kind of easy because we picked QP. So if you pick the number 1, it's going to be what we want. But let's say we don't know it, or let's say that we want to know for a different point. So then here's how you would find it, right? If you don't see it right away, if you don't want to guess, this is how you would do it in general. So solve for T. R of T equals the vector for P, which is 2, -1, 4. This is the position vector for P, right? And then I just gotta solve for this. Now, how do I solve for this? Well, you solve for this kind of like you solve a regular equation. So vectors equations are easy. You can still add, subtract, multiply by things. The only thing you cannot divide, you can do is divide by a vector. But other than that, see, this is not hard. So what is R of T? Here's our formula for R of T is 306 plus T times -1, -1, -2 equals 2, -1, 4. Right? So I want to solve for T. So I subtract this vector from both sides. 2, -1, 4 minus 306. And this is 2 minus 3 is -1. -1 minus 0 is -1. And 4 minus 6 is -2. Right? And then that's super easy. What T should I multiply this vector so that I get the same vector? Well, 1. So T equals 1. Now, if you had gotten a different one here, then you can still figure out the T just by looking at, say, the X or the Y or the Z. You just pick one of them. Any one of them will work, right? So in this case, T equals 1. So then the answer to this purple, the question is that the equation is the same, but now T goes between 0 and 1. So here's the answer to the additional question. The vector representation is the same, 306 plus T -1, -1, -2. And now the difference is you want 0 as T between 0 and 1. All right? Questions so far?
Yeah, Professor.
Lines will be very important. And the other, so lines and circles are kind of like our basic way. So that way that I showed you earlier about doing cosine and sine are important. So X coordinate cosine, Y coordinate sine describes a circle traversed in the positive direction. And then this is how you can get a line. All right? So now we're going to look for the rest of the class.
Professor.
The rest of the class, we're going to look at different, we're going to learn how to graph or how to get an idea at least of how other types of vector functions look like, how the curves look like. So let me start by looking at example 2. Let's go to the book. And so this is what we want to do. It says, graph the curve described by the equation, and you have it right there. Oh, notice a little difference with this one. So you can write it with components like we were doing right now, right? So the X component, the Y component, or the Z component. And let me see, I have a question right here. How did you know QP was ABC? And Michael asked for the previous problem. So let me go back to the page. So in general, that's, so when you want to do a line, you want to find a direction vector for this line. And there's many that work. So I chose from Q to P, but you could also do from P to Q, Or you could even do from P to Q half of that, right? It doesn't need to be the entire length. Maybe you want it half as big. Or you can do from P to Q times 10, 10 times as big, right? So there's many, many choices to pick the direction vector for the line, right? But the two easiest are to pick either QP or PQ. Those are the two easiest ones, all right? Mm-hmm. We have variability of choices here. So it's like too many choices, which makes sense because it's the difference between going through the line at 10 times the speed or at 1 time the speed or at half speed, right? It is also the difference between going this way or going the opposite way. Mm-hmm. So tons of choices. That's a good thing, right? So there's not a unique way of doing it. There's many, many that work. Mm-hmm. Great. Let me go back to our problem we're talking about. Oh, yes. So I was telling you here that you can write, maybe I'll write it in a moment. So for this example, example 2, you'll notice that it's written in the book with I, J, and K. And you can write it with I, J, and K, or you can write it with the components, the X component, the Y component, and the Z component. Both are acceptable ways of doing it. And it's just a matter of taste, right? Which one do you prefer? Which one looks better to you? Okay, so that's what we want to do here. We want to graph this curve. We want to graph the curve. Let me put it over here. So it's R of t equals, I'll write it first with the I, the J, and the K, and then I'll show you the alternative way of writing it, T over 2 pi K. And it has two possibilities. One, if T is between 0 and 2 pi, and B, if T is between negative infinity and infinity. All right, so let me go back to the page. And this is what I was telling you. You can write it like this, or you can write it like this. It's the same. It's like different way of writing things, because we already know that I is the vector 1, 0, 0, J is the vector 0, 1, 0, and K is the vector 0, 0, 1. All right, so you can do it like this or like that. Either way is acceptable and correct. Okay, so now let's see if we can understand what this is doing, right? And I'll show you some better graphs in a moment, and I'll even let you know how you can figure this out on your own as well. What tools do you have available to do it? So first, this part over here. See, it kind of, let's just look at the X and the Y. See, and that's useful. It would be like what happens when we look from the top, right? So we know this picture is in 3 space, but imagine that you look from the top. So this is the view from the top. And if you look from the top, then all the Z's don't really matter, and you're only looking at these two. And this sounds familiar. It's like X is 4 cosine T, and Y is sine T. It kind of looks like the circle I described at the beginning of the class. The difference is that that circle only had, it had the same numbers here, right? 4 and 4. And this one has 4 and 1. So the only difference is that then this circle is elongated on the x-axis, right? It's 4 times as long on the x-axis as it is on the y-axis. So it's not really a circle, it's an ellipse, right? So when you do things like this, it looks like an ellipse. Specifically, you go 4 units this way, -4, but only 1 unit this way. So it's gonna look like this. Like this ellipse that I'm drawing, more or less. And this is how it looks when you go from 0 to 2 pi. You go once around this ellipse. If you insist that T keeps going, then you just go around and around and around and around, right? You're just overlapping the same ellipse. Now let me convince you that it really is an ellipse. Something you can do is solve for cosine and sine. So x over 4 is cosine and y is sine. and then square them and add 1. So you get x squared over 4 plus y squared equals cosine plus sine squared plus cosine squared, which we know is 1. And if you remember from high school, this is exactly the equation of an ellipse, right? Of an ellipse where the semi-axis for the x is of length. It's actually length. Is it length 2 here? Plus length 4, right? Or did I? There's something that I didn't do right. Oh, when I square them, it should be 16. 16. So that's why it's 4 times as big, right? Mm-hmm. Okay, so this is what it's doing, right? So the x and the y are just going around like this. Now, what happens with the z? Well, the z is simply growing in a linear way, right? There's the 2 pi. So as you go from 0 to 2 pi, the t over 2 pi will grow from 0 to 1. Yes? So think of it this way. This is going to be like this. As you go around, you're also going up. You're also going in the up direction a little bit. And then once you go once around, you're actually 1 unit higher. Does that make sense? Yeah? Okay, so let me show you on my computer, on Mathematica. I just put the function that we wanted to do. You can see it right here. You'll notice that I wrote the function that we wanted. Is 4 cosine t sine t, t over 2 pi. And then there's a bunch of other things there that it's just about how to write. I wanted to put the arrows that show you the x and the y and the z axis, and I wanted to make it a little dynamic. So you don't need to pay attention to the rest. You just need to know that that's the function that I'm drawing, all right? So I'm gonna clear it because I need to move now. And here's how it is. So these are the axes, right? And the z-axis is the one that is pointing up. All right, so as I go around, just like we said, so between 0 and 2 pi, this is exactly what happened, right? Let me run it from the beginning. Okay, so between 0 and 2 pi, I'm too close, let me back a little bit, still more. All right, that's good. So just like we were saying, between 0 and 2 pi, it goes around in the form of an ellipse. And after you're done after 2 pi, you're exactly 1 unit high, right? Let me show you, right? The view from the top. How does it look from the top? Hey, just like an ellipse, just like we said, right? I mean, I'm kind of crooked. Maybe let me move it this way. Good. So there it is. It looks like an ellipse, right? And then when I take it back so we can see from the side, this is what happened. So as we were going around, it went 1 unit up. Is that clear? Yeah? And more importantly, do you see what's going to happen if I keep increasing, right? If I don't go from 0 to 2 pi, but if I keep going, say I go now to 4 pi. If I go to 4 pi, and I'm going to keep going now another way around, and then when I'm done, I'm going to be 2 units up, right? Because the t over 2 pi is increasing. So now is the t right here at the end is 4 pi. 4 pi over 2 pi is 2. So now I'm 2 units high. Is that clear? And if I keep going, well, that behavior continues. So this is kind of like what is it? A spring, right? A spring, but it's not in the shape of a circle. It's a spring that it looks a little bit like a flattened spring. See, look from the top how it looks. It looks like an ellipse, right? The ellipse that we were talking about. And look right here. how it's, winding around. And also, if I go to negative values of t, then it just goes in the opposite direction, right? Just like I'm showing you right now. So this is the overall graph of this nice graph. It's just a spring that is sort of flattened. A spiral is the correct mathematical term. It's a spiral in the shape of an ellipse. Let me turn it a little bit so that we have the positive axis facing us, because that's the picture that you will find in the book. And I'll show you the picture from the book, the analysis that they do in the book, and how is it essentially the same as what we did right here. So this is more or less the way it looks in the book, okay? And you don't, I want to stress a point that you don't need to have a computer to graph this. I mean, it helps because then you could do things like I'm doing right now, right? Like take it back, how it's, so you can see what happens as the t changes, right? As the t increases, how is it that the graph is drawn, right? From here, and it goes up, 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 and how it goes around and draws the graph. So that part is nice, but in essence, we knew what the picture was going to look like from even when we were doing it on the page, right? Just from the page, we already knew what was going on. Okay, so this helps, but it's not necessary, is the point that I'm trying to make. Let me show you in the book how it looks like, and then I'll give you choices of how you can figure these pictures on your own as well. So here's the picture from the book. It looks a lot like the one I just showed you, if you see. So this is first the view from the top. We kind of knew it. What happens when you go once around? We knew that too. So at the same time that it's going around, the height progressively grows. Yes, so you go around and now you're 1 unit up. And if you keep going, this is 8 loops of that, then it looks like this, right? Goes around, goes around, goes around, keeps going around, and so on. Okay, so let me, I wanted to show you how you could do this yourself. And what you can do to do it yourself is you can go, let me open another tab here, to Wolfram Alpha, and to visualize these things. And so here it is. So just go wolframalpha.com, and you can write down the parametric equations that you want to calculate, right? So you can just write plot, right? And then the equation that we have, right? 4 cosine t. You can use Mathematica will understand. Doesn't matter if you use capital letters or not for the sign, etc. And then t over 2 pi. And then you tell t between what and what? T between 0 and 2 pi. Okay, didn't understand that I wanted. Okay, so this is what it did. It plotted the 3 equations at the same time. It didn't understand it as a vector, right? So maybe we should put, the parentheses like this. Maybe that way it understands it's a vector. Still no. Okay. Okay, maybe I don't want plot. Okay, I think it's parametric plot, I think is what we want. Yeah, there it is, right? And you have it right here. So this is once around because we did it between 0 and 2 pi. If I make it between 0 and 10 pi, it will go around 5 times. And there you go. So this is all always available to you, and it's free. You don't need to pay, and you can, you know, figure it out. You just need to enter it like this with parametric plot is the important thing. All right, good. So that was one of them. Let's go back to the book, and we'll show. Whoops, what did I do? All right, so here's our next exercise, example 3. This time we want to graph this curve. And they're already sort of giving us a little bit of a hint of what this is going to look like. It says the roller coaster curve, and it says R of t is cosine ti plus sine of tj plus 0.4 sine 2tk between 0 and 2 pi. Okay, good. Go to the page. Put a bit more. Okay, so this is the one we want to do. And see, now again, if we want to do the x view from the top is easy because it's just a circle. This time they're even the same, right? Cosine, sine. So that's just a circle of radius 1. Like this. So that's how it looks when you view it from the top. But what is the z coordinate doing? Sine of 2t. Let's do another graph over here of the z. So this is going, I'm going to graph t over here between 0 and 2 pi. And over here will be the z. So I want to know what's happening with the z. And sine oscillates between -1 and 1. But we're multiplying by 0.4. So this will oscillate between 0.4 and -0.4. And it's the sine function. So we know the sine function. It just goes up and down, up and down. The difference is we're multiplying it by 2. So that little 2 over there is going to make it go up and down twice as fast, right? So it's going to be like this. Up and down, and then again. Up and down, up and down. Okay? So I hope this is enough for you to already visualize what this one over here is going to do. See, this is what it's doing. On the x and the y, it just goes around as a circle. And then, at the same time that it's going around as a circle, it's going in the z direction. It's going up, down, and up again, right? So it's going to have 2 points that are higher, right? So you're going around, and there's going to be 2 points that are higher and 2 points that are lower, right? Are you visualizing already? Getting an idea of what it's going to look like? Yes, so we go around, but we go up, then down, then up, then down. Okay, so 2 high points, 2 low points. And I hope you're already thinking about what it's going to look like. I'll show you in Mathematica. Where is it? Right here. So it's the next example that I represented. So it's right there. And it goes around, and it goes up, then down, then up again, then down, then up again, right? What is that, the graph of? If you said Pringles potato chip, you were a winner. That's exactly what it looks like, right? See? It's like a chip, right? A Pringles potato chip. Yeah? It goes up and it goes down. If you look at it from the top, it looks like a circle. I should probably move further back so you can appreciate that it's a circle. But the view from the top, so it looks distorted a little bit right now because the point of view of the camera is too close to the graph. But if I go further away, it's gonna look like a perfect circle. And so just like we said, up, down, twice, right? Neat, right? So we can now graph different types of shapes that we couldn't do before, and describe them, in a relatively easy way. Now here, if we keep going more than 2 pi, nothing happens, because the thing that's happening is we go over the curve again, right? The book called it a roller coaster graph, because you go up and down, up and down, up and down, and you keep going like that, right? It's a never-ending roller coaster. Let's modify it. See, that's the good thing about having something like this, which you can also explore in Wolfram Alpha. What do you think is going to happen if we change these two? What would happen if we make that 2, say, into a 4, right? So we make that into a 4. What do you think is going to happen? Remember, here's a graph, by the way. Right, that's the equation of the graph. And now I made it into a 4, right? And the question is, what do you think is going to happen? And if you said, so what would be the difference? The difference is, if we go back to the page, the difference is that this one over here will now go up and down, up and down, up and down, up and down more times, right? So you would still be going around like this, but now the up and down will be more, right? We're gonna now have 4 times where we're up and 4 times that we're down. Exactly, more ups and downs. And so let's take a look at it. It's can't keep up with the suspense. So if we run it, and then up and down, and yeah, it would be a different design of potato chip, right? So it goes up and down more times, 4 times as to be exact, right? So there's four high points and 4 low points, right? And that would happen, right? If I make it 10, that's a lot of ups and downs, right? You'll see. Kind of like a crown, right? A crown, when you go up and down, up and down, up and down 10 times. And also this 0.4 tells you how high and up you're going. So the difference is 0.4. You want to make those up and downs less, then you can change the 0.4, right? We can change this 0.4 to 0.2, and then the up and downs will be less intense, right? Or we can make it bigger, and then they will be even further apart. Okay, good. So let's just leave it where it was for the next time that I need it. So it was like this, and with a 2, go back to our Pringles potato chip. Yeah. Okay, very good. So let's move on to the next one. So first, here's the diagrams from the book, as you can tell. So here's the view of the Pringle graph and how you can, I mean, we didn't do conics, but it's the intersection of this cylinder with this hyperboloid. But we didn't cover any of that, but it's interesting nevertheless that you can find it as the intersection of 2 curves. So this is the next one we want to do. So this one is now 3 plus cosine 15t times cosine t. 3 plus cosine 50t times sine t is the y component, and the z component is sine of 15t. Okay? Let's think about that one. So what is this one happening? Well, this is a bit harder to explain without looking at the graph, but we'll give it a shot. So first, let me write it here. So let's go back to the page. So this is the one we want to do now, is R of t is 3 plus cosine 15t times cosine of t. I'm going to write it like this, which is the one I prefer, times sine of t and sine of 15t. And t is between 0 and 2 pi. All right, so what's the story? What is it that we have? Well, this is kind of harder to understand because this product is not clear what's happening, right? So we'll give it the z coordinate we understand. The z coordinate is sine of 15t. So the z coordinate, so this z coordinate, if we draw it as we did it before, is gonna oscillate between -1 and 1. And the thing is, it has this 15t. So that 15t is gonna make it so that it goes up and down many, many times, right? 15 times. So I'm not gonna be able to draw it, so I'm just gonna start it, but it goes like this. And keeps going on like that till it finishes like this. And it goes up and down 15 times, all right? Up and down 15 times. I don't wanna do all of them. Okay, now what about the x and the y? Well, the x and the y, or let's just look at the x. So what's happening with the x? It kind of looks like the cosine function, right? But where you're multiplying the cosine by this number. Now, this number is, this is between -1 and 1, right? So when you add 3, it's going to be now between 2 and 4. So all of these between 2 and 4. So the x coordinate is kind of like the cosine, so the regular cosine function. So the regular cosine would look like this. Would look like that, where this is 1 and this is -1, but it's not the regular cosine function. We're multiplying it by something between 2 and 4. And that thing that we're multiplying it by oscillates. Sometimes it's bigger, sometimes it's smaller, right? Sometimes you multiply by 2, sometimes you multiply by 4. So this is just cosine. This is just cosine of t. So if you want to know how this one looks like, it kind of looks like we said, we go from 2 to 4, and -2 to -4, and at the same time that we go between those two, we sort of follow the shape of cosine, but this makes it go up and down, right? So it's going to look, I can't draw it precisely, I'll show you soon, but it sort of goes up and down, So, and in a sense, following the shape of the cosine, right? With ups and downs. How many of them? About 15, right? About 15 ups and downs, right? So the x and the y coordinate, except from those little oscillations, right? Let's go back here. So we have this part over here that makes it deviate a little bit from the regular cosine and the sine. But if we didn't have that, if it was only like this, cosine and sine, then it would be something that goes around only, right? It would be like the circle, like all that simply goes around. So take a look. Let's take a look at the shape now from Mathematica, and you'll see. So Okay. So the X and the Y, what's happening here? Too close. I need to be further away because things happen that are between 2 and 4. So, okay, there we go. So here is what's happening. As the X and the Y sort of go around, but they have some isolations, and the C goes up and down, up and down, up and down. And this is the shape. Neat, right? So it's from the top, it looks like this. So like I was telling you, the X and the Y, go up and down in this symmetric fashion, right? So it looks like this, but in reality, it's a curve like it's kind of like well, the description of the book is actually correct. It kind of looks like a slinky, right? A slinky that where you put the two ends together. Mm-hmm. A slinky where you put the two ends together. And let's get a little closer there. Mm-hmm. Too close? No. Okay, good. Still too close because some parts are broken right there. So that's the best where I can show you the entire thing, and you can see how it looks from different points of view. Mm-hmm. And then it's symmetric, so and periodic. I mean, so if we continue drawing it further, it just goes on top of what we had traveled already, and you don't get any more of the curve. It just looks the same, right? So here's how we do it. Mm-hmm. So goes around and it winds up on itself. Mm-hmm. And you can tell now what would happen if we alter some of these numbers. So if we make these 3 bigger, we're gonna just make it so that the shape of the hole will be more or less the same, but the outside part will be bigger, right? And similarly, if you change the 15 to say something like 20, then it's gonna have more loops in the slinky, right? I mean, let's do it. Let's do 25. Let's put 25 here, and 25 here, and 25 here, and see what will happen. Yeah. So now instead of going 15 times around as we go here, it's gonna go 25 times around, right? And the same thing, you wanna do less, let's see that it only goes 5 times around. We can change the 15 to 5, and now it's gonna look like this, right? Now it doesn't look at all like a slinky, right? Because it barely has a chance to wind itself over itself, right? So not as pretty as the way we had it with 15. All right, and we have one more that I wanted to show you, which is also ties it with the concept of calculating limits. And so I'll skip over the limits part for next class. So I won't tell you right away. It's actually quite simple. But instead, I want to take a look at this example 5. So example 5 in the book, let's go to the book, will be the last thing we do today. And so page 873. Well, first, let me show you the picture of the one we just did from the book. So this is the better picture of what I was telling you right here on the left of how the X component looks, as T goes around. So you can see it sort of follows the cosine shape, but it has the ups and downs. And if we could do the Y, it would follow the sine shape with the ups and downs. then this is how the curve looks, and it's on the boundary of a donut. The correct mathematical term for donuts in math, it's a torus. This is what we call this shape, and it's in the surface of a torus. And this is the view from the top, right? The view from above. Good. So let's take a look at the last one. So the last one is, again, going to have the traditional cosine and sine for the x and the y. So we know it's going to wind, right? And you can see it right here. So we have cosine pi times t, sine pi times t. And this is the new one, is e to the negative t, right? E to the negative t. So let's take a look at how the graph looks like. So this is what I have, is cosine pi t, sine pi t, and e to the negative t. In mathematics, you need to put exp for the exponential function. And this is what it looks like. So it winds around, winds, and winds, and winds, and winds, and winds, and it's still winding, but it's sort of reaching a limit, right, if you think about it. And that's because the height is e to the negative t. So when t goes to infinity, e to the negative t goes to 0. And that's the point we want to illustrate with this. So we want to illustrate the concept of limits. And so we'll pick it up from here next time. We'll take a look at how this one looks like. So it's something that at the same time that is winding in the x and the y from the top, it looks like a circle, right? But as on the z coordinate, at the beginning, it slows down quickly and then it goes to 0 and then it slows down. So then we just wind and wind around. Here it is. Okay. So it goes around and around and around, and it goes going around and around and around. And this illustrates the point that we want to illustrate is how to get the limit, right? What's happening with the limit of this when t goes to infinity. Good. So we'll pick it up from here next time. Tomorrow we'll finish this and start talking, of course, about calculus on vector values functions, which is really what our interest is, right? I mean, this part today was exploratory, and we just show some nice pictures, and how we could figure them out. Tomorrow will be a bit more formal and start calculating things like limits and derivatives of vector values functions. All right. Good. So I'm a little bit already over time, so I'm gonna stop right now. Okay, guys. See you tomorrow. Stay safe.